So if you check the Slack workspace, it's actually exactly what I posted yesterday, that it was the slides for day one. It's actually the same link for slides for day two as well. We're just going to start from the middle. So if you open it up and press escape, you can get the slide sorter view and skip ahead to slide number in a minute. So these are all things we did yesterday. We attempted to do exercises 2, 3, and 4 yesterday. Today, I want to start at slide 34 with environment modules. So, welcome along to part 2 of Introduction to HPC. The first thing we're going to kick off today with is, how do you use software that somebody else has provided for you? So most, in fact, if you go to the top 500 sites, all HPC systems these days, 500 out of 500 run Linux. And the people who make the Linux distributions, for their ease of software maintenance and security updates and things like that, would rather you only used one version of a piece of software at a time. So if you're using Bash 4.3 or whatever, that's the only Bash you will have available on your Red Hat Enterprise Linux. And that works for, say, well, it works for enterprise. It might work for a single researcher who's only got a fixed number of things they want to do with a fixed software. I'll use the word software stack here, and I mean the dependencies between bits of software. There's a very famous XKCD cartoon of the infrastructure of open source, and it shows lots of rectangles stacked one on top of another with one small vertical one, looking very precarious. So a software stack is all of the dependent bits of software. Researchers need different software stacks when they're doing different projects. And also, if you're an HPC center like we are, and you're providing resources to 1,000 users, you've probably got 2,000 different software stacks, maybe not all unique, but 2,000 different ones that need supporting. And so we can't have that system where you've only got one version of each major piece of software at a time. So this concept came about, environment modules, from the needs of HPC. And basically, you install multiple versions of the software in different parts of the file system, and then you manipulate the environment variables of the shell to point to the version you want to use. The original granddaddy of them all was a thing that's, I think it was just called modules at the time. It seems to be called environment modules now. It's a boring implementation detail that you don't need to know that it was implemented in the TCL language. The only reason I say that is because it enables you to distinguish it from the newer implementation. Does exactly the same job, a few added features and a few niceties. LMOD, which is implemented in Lua. So some people say the TCL modules or Lua modules. Some people say environment modules or LMOD. Two different versions of the same thing. CSD3 has been around a while. We're old school, so we use the environment modules TCL version. I'll jump over to the shell at this point, see what horrible stuff I've got. Let's see if I can log into. So first thing is make this big enough for people to see. Is that okay? I wonder if there's a way of getting rid of that thing on the side. Is that big enough at the back of the room? Yeah. Okay. Again, you'll be logging in, you'll be SSHing to login.hpc.cam.ac.uk. I do it so often, I set up a convenience alias in my config. And because I work for the university and access the system a lot, I need a second factor to log in. There you go. Are you a University of Cambridge person? Yes, you do need a second factor and it should work. What's not working? Sorry? Actually, give me a second because mine is not working either. It's, they roll over every 30 seconds, and the system does, yeah, it gives you enough leeway for the old and new codes so they sort of overlap. So I had to give it 2 goes to log in. So give it a second go. Oh, so I set mine up like about 4 years ago, so it might be different now. Nero, can you help the idea? Yeah. Anyway, whilst those two figure out logging in, I'm going to talk about how you find bits of software. So if I wanted to, LS is probably a bad one because my home directory is just awfully messy. So let's try cat instead. It doesn't like cats. The question is, what program gets executed when I type in the command line? And you can find that out with the command which. And the cat, if I type cat, the one that actually gets run is located in user bin cat. If I type, now my brain is just going to the example. It won't matter if I show you the, if I spoil it and show you the answers. If I wanted to run H5 perf, that's not there, can't be found. The question is, and I know it is there. I know we've got like at least 30 versions of H5 perf sitting on the file system. Why can't it find it? So when it's trying to find the system, it looks in the following directories, which are in the environment variable path in the file system, which is quite a lot. They're just all smushed together with a colon in between them. So if I change the colons into carriage returns, with that cryptic string, you don't have to. There. Thank you, Tom. And yeah, you don't have to memorize sed commands. That's just to show you that's the list of when I type cat. First, it's going to look in my poetry bin thing, which has nothing to do with poetry. It's going to look in my cargo bin. It's going to look in a whole bunch of directories which start user local software SPAC. I'll come on to that in a minute. It's going to look through all of these. Eventually, when it hits user bin, it will find it. So that's where it's looking for cat. When it's looking for H5 perf, it's also looking in those same directories. I can manipulate the contents of the path variable by using the modules command. So if I type module list, here are the ones that I've got loaded by default, and you should have a similar list. Some of these are sort of super modules in the sense they pull in other modules. So the rel 8 global will actually pull in some other modules, and the rel 8 default ICL was the one that's pulling in modules 876, 5, etc. So if I want to access the H5 perf command, I know it's part of H5. So I look at all the modules that are available for the command module avail. If I just hit enter, I'm going to get all of them, and it's going to take a while. I will in fact do that because the first time through, it'll find them all and it'll cache them. Following times it might be faster. So I do that. It's going out and looking in the file system and finding all of these bits of software and the various versions which I could load, and it's still going. So I'll quit out of that. It'll take a second. There is tab completion in the module system. So I know that HDF5 starts with, if I type H and hit tab, it's going to do a lot of searching in the file system. So I'm going to go all the way through inside HDF5 and then hit tab. And those are possible ones I could load. in the exercises, I've given you a short one. You see, the very top one says HDF5/, and that's sort of like a subdirectory in the module system. And let's go for 1.12.1. So that one's available. So if I load it, and now say which H5 perf, it hasn't found it. And this is another reason you might use modules, because you can compile bits of software in different ways with different options. And so the particular one I loaded there, 1.12.1 or whatever, doesn't have the parallel version of H5 perf. So the sysadmin at the time it was built it only for serial. So there is one there, and I can run that command. Likewise, slot it. Okay, so that's a command I couldn't have run before I loaded the module. Now I've loaded the module, I can, if I module unload it, HT, and then try running the command again. I expected that not to work. Anyway, we'll go back to the slides and move on. So, slides. One thing to note is, question. Yes. Yes. It is, but it's not available in the TCL mod, which is the one that we've got. And I was thinking what I was going to say this morning in this section, and I was wondering, am I going to talk about module spider, and am I going to say what a weird name for search that is? Because you can't say module search or module find, you say module spider. I have no idea why they chose that, but yes. So there are slight differences between LMods and environment modules. That's one of them. So nicer features for discoverability in the newer one. The other thing you'll find is the exercise we're doing today could be useless when you go back to your cluster, because the module names are site specific. There are different conventions about, whether you put the name of the compiler stack in the module name or not, and if you do you put it before or after the version number? Do you add other stuff? So that's just one thing to note. If you get a job script from a collaborator somewhere and it's got module names in it, you're probably going to need to rewrite that bit for your cluster. The other trap is that the output from the original environment modules, instead of going to standard out, goes to standard error. You can't really notice a difference when you type the command on the screen because you just get the text, but there is a difference when you go to pipe something, like if you want to pipe it to grep to searching because your modules is too old to not have spider. So if you've got the really old modules like we have on CSD3, that's the cryptic thing to actually grep the output. You have to redirect standard error to standard out and then grep it. It's messy. It's something you need to know. So quite often you'll be prototyping stuff on the login node. You'll be discovering how you want to do things. You'll have loaded a particular set of to get your work done. And then you want to do it 1,000 times or 10,000 times or 1,000,000 times on the compute nodes. You do need to remember to put the modules that you need in your job script, because they won't be loaded, at least on our system, they're not loaded automatically. The other thing I put is falling off the bottom of the screen. And this is a personal thing. I prefer to module purge before I load the modules that I want, which means I don't get any of the default ones. That's more for sort of reproducibility. So I know exactly what the software stack I needed was to get the job done. So that's environment modules. Give it a go. Log into CSD3, run module list to see what you've got loaded by default. Run module avail to see all of the things that are there. If you get bored of it, press Q to quit out of it. It puts it in a pager. Try running H5perf serial, it will fail. Try loading the module by doing it again. That should only take 2 or 3 minutes. So I'll give you some time to do that. If you have trouble, stick your hand up, someone can help. No question. Question. It's a site policy thing, and it causes internal consternation in our group. It's not my job. I don't care. It's the sysadmin who's put their foot down, and I do actually agree with their stance that they'll never remove an old module. They'll only add to them. Because the problem is we've got 1,000 people all writing job scripts, handing them down to the next postdoc or the next PhD student or whatever. Some of those job scripts are really old. They load really old modules, but they still work. If they still work, we should, may as well keep them around and not proactively break people's workflows. It does mean that we have an awful lot of modules. If you go to another HPC system, so you go to Tersa in Edinburgh, you get nothing. I think you get compilers and CMake, and that's it. Yeah. Yes. I thought I might explain it, and then I ran out of time just to stick a slide in. So that those are actually paths. Those are where the modules can be found. And we've installed them different ways. So some of the bits of software have been built by hand. So somebody's downloaded the tarball, untarred, gzipped it, and done make check, hopefully, make install. And I used to do that at the beginning of my career. I used to do that, and it was a tractable problem then. I won't tell you when that was, how many years ago that was. A long time ago, you could do that because the dependency tree was much smaller. Nowadays, if you want to build a complex piece of software, it might depend on 10 things, each of which depend on 5 to 10 things, each of which depend on, and the tree of dependencies is massive. And the range of compatible versions of those dependencies is quite hard to find an overlapping set that works. It's a problem everyone has, and 2 people have solved. Well, multiple people solved, but there are 2 popular open source projects. So Kenneth from Belgium has solved it with a piece of software called EasyBuild. And so some clusters come by default with software deployed with EasyBuild. And you'll note that you'll be able to detect that because I think the path names have E-EB in them somewhere. The other person who solved it, the other person who was annoyed enough to solve it and write some open source software and put it out there was Todd Gamblin from Lawrence Livermore, and he made a piece of software called SPAC, which stands for the Supercomputing Package Manager. And so we've actually used both. We have used EasyBuild on the Secure Research Computing platform and SPAC on CSD3. We're now moving to just using SPAC everywhere. Right, I think we'll probably move on because, yeah, we've got more stuff to look at. So, array jobs. What happens if you want to do a very similar thing an awful lot of times? This happens a lot in scientific processing. You've got a job script, and maybe only one thing needs to change. The index of the, well, genome's probably not here, but maybe the index of the level in the atmosphere you're looking at. Or you could actually have 2 things that change or 3 things that change, but as long as you can map them onto a sequence of integers, you can cope with running all those 10,000 jobs without writing 10,000 job scripts. You just write one job script. And this is the same thing we've seen earlier, except that we've got a new line here, line 5. No, sorry, where is it? No, nothing's changed in the directives. So those are all as we saw them before. I've just changed the job name. It's when we launch the job script, we say SBatch, and here I'm just going to launch, I'm going to do a fence post error. 10 of them, 1 to 10, yes, 10 jobs. Each job is going to be running this job script, but the value of this environment variable will be different in each instance of the job. So the first one, Slurm array task ID will be 1, the second one, Slurm array task ID will be 2, etc. The last one, Slurm array task ID will be 10. One thing to note is that this works really well if all the array members are independent, because there's no real control over when they execute. You throw them all into the scheduler, and the scheduler will fit them in when it can, and the order isn't necessarily guaranteed. So you can't say that 1 will execute before 10. They could be executing simultaneously, or 10 might execute first. That's unlikely, but you can't guarantee it. So what I'd like you to try doing is submitting an array job. You can just copy paste. If you're quick enough, you'll see what it looks like in the queue, or you could add before or after the hello line, you could add the bash command sleep with a number of seconds, like sleep 10 or sleep 20, whatever, so they stick around in the queue a bit longer. But have a go at using an array job, look at what it looks like in the queue, and then look at what you wind up with in the file system. And you had a question? Yeah, so if you're curious about what I did wrong yesterday, it wasn't Stuart's fault. You get the good bit. I missed out what's there, line 6. So specify a partition. We've got the Cascade Lake partition by default. Unfortunately, the nodes that were reserved for us were on the Ice Lake partition, and the scheduler couldn't match those up, and Stuart said no. So today we are specifying partition equals Ice Lake, and it is working. Yes. Which you need to know if you want to cancel them all. So if you launch 10,000 jobs and you look at the first one and go, oh, no, that's not right, you don't want to have to be typing 999 lots of S cancel or whatever. So you can address the entire array with that underscore notation. I will push on a bit because we've got a few more, we've got cooler exercises coming up. This one was okay. I don't know if anybody in the audience thinks this would be a useful thing for them in their work. This is a very simple example of a workflow, composing more than one job to do a campaign of computing. It really only works if your jobs are independent of one another. I did mention yesterday that you could use some features of Slurm to run dependent jobs one after another, if after one job succeeds, or you can actually also run a job if a preceding job failed. But those are very basic features with which to try and cobble together a workflow. Your computing campaign might be more complex than that. Do not be tempted to write your own workflow orchestrator. I know it's a terrible temptation for academics because I've been working in this career for a while and I've seen lots of them. Everybody starts with, oh, I need to do this simple thing. I'm not going to investigate a proper workflow thing. I need to do this simple example. And then over 20 years, their thing grows to a behemoth of 2,000 lines of bash, and it's impossible to debug. So the idea is people have solved this problem. Be aware that the solutions exist and use one of the solutions. It's very tempting to write your own, just don't. So ones that I can recommend are Snake and Nextflow. The advantage of this is if you have your own custom scheduler, you can't collaborate with people at other sites who don't have your workflow system. Whereas these two implement a thing called CWL, the Common Workflow Language. And so those workflows are portable. You could give them to somebody else and they could reproduce them at their site. I've linked the advice from NERST to their users about what to do about workflows. They actually list about 6 or 7 other workflow systems. I just listed SnakeMake and Nextflow because from my experience, those are the ones that are most common and most popular. It's a shame Tom walked out of the room because this is the bit he contributed. We're going to talk about how you program high-performance computers. So previously, we've just been running simple bash commands like echo and sleep, which isn't particularly high performance. And our job scripts have been saying nodes equals 1, cores equals 1, which is also not very high performance. Your laptop's got more than 1 core. So how do we make use of all of the computing resources we have available to us in a high-performance computing system? Well, we need to program slightly differently. If you take a serial program that runs on your laptop and run it on a supercomputer, chances are it's just going to run on 1 core and not you'd be wasting 99% of the node. There are various approaches, and there is no one approach that everyone uses. Back when I started, there was one. Well, actually, there were 2. There was a thing called PVM, which no one uses anymore, and MPI, which essentially won. And that was the way you programmed HPC systems. But it didn't suit everybody, and they've come up with other methods. This one works if you have a shared memory system. So the easiest way to think about that is in one single server. So all of the tasks of your OpenMP program need to be able to communicate with one another by reading and writing memory in the system. So they all need to have the same view of the global memory. And so you get that usually in single systems. And if I gave this talk 10 years ago, I'd have said, be wary of that because, you've only got access to 2 or 4, or maybe if you push the boat out, 8 cores. Now we've got a single server of 256 cores. You can actually get a lot of computing done in just one single server these days. Another thing to note is the word specification there. So the OpenMP architecture board, ARB, the architecture board write out the list of rules for how OpenMP should work, and then other people implement it in their compilers. So there isn't one version of OpenMP. Every compiler that supports it is a separate implementation, but they should all work the same way, and the way they should work is specified by the OpenMP ARB. And it was originally they show a graph every year when they do their talk and show you the size of the specification from version 1 through to version 5. And version 1 was quite short, and version 5 is getting massive. This is what it looks like. And apologies for those of you who don't read C. It's only 11 lines, and some of them are blank. So I'll talk through it a bit. A normal C program would look exactly like that, except it wouldn't have lines 2 and 5. And so line 5 is more characteristic of how OpenMP works. It's a directive-based programming language. And so the thing that says hash pragma isn't part of the C language, but it's a special instruction to the compiler to say, do something compiler specific special with what follows. And when you're telling the compiler about OpenMP directives, you say hash pragma OMP, and then the thing that follows that is what's specified in the OpenMP standard. And I'll talk through that a bit. I'll just wave away line 2, which isn't a directive. There are some convenience functions and values, constants defined that make an OpenMP work. And if you want access to those, you have to include the header omp.h. And so, for instance, the function call on line 7, omp get thread num, which is a little bit like the slurm task ID we had previously. That's defined in omp.h. So what happens, you notice that on line 6, below the directive, there's an opening curly brace. That's a block. That opens a block in C code, and the end of the block is 9, line 9. So that pragma applies to basically lines 6 to 9. So it's saying start a parallel region, start up as many threads as have been asked for or are available, and do that block in each of them. So that's the hello world of OpenMP, that program. You would compile it with a compiler. Here we've used GCC. The only thing different to a normal compiler invocation is that -f OpenMP flag. So you've got to tell it that you want OpenMP. If you leave it out, it'll still find omp.h probably, and it'll ignore the pragmas, and you'll just get a serial version of the same code. So one place people use OpenMP a lot is starting with some serial code and progressively adding parallelism to it, because you can do it in small chunks. So, and Tom's probably frowning because it wasn't the exact slides he gave you yesterday, but I've switched it up a bit because I'm going to make people do this as an exercise. Can you predict what will happen when you run that program with 4 threads? The way you do that, you compiled the program, the line we had earlier. You set an environment variable omp_num_threads. So for instance, to set it to 1, you'd say export omp num threads equals 1. If we ran export omp num threads equals 4, and then built that program and ran it, what do you think will happen? And you can get, spoiled it. Okay, I'll put it back here. So the exercise is, and don't skip ahead in the slide, the exercise is copy that program. It's in the repository. So if you git clone the repository, I should put this in the slash. You can cut and paste it in the slides. It does work. But, so as before, if you're running into difficulty, stick your hand up, Nina or Tom, or I will help. Git clone the repo or copy and paste from the slides. Use the command to compile it, GCC -f OMP, OpenMP -03 hello.c -o hello.exe. Sets the number of threads to 4. Think about what might happen. I think we'll move on. Because we've got a couple more exercises to do. I do want to get to the very last one, which has got no programming in it at all. You just go to a website and type some numbers in, but I think it's possibly the most important one of the day. And so you might have to skip some to get to it. What happened then was we ran, hopefully we did that, taking the $signs out of the front of them so the commands actually worked. And this particular time that the program was run, we got the results in the order 1302. If we ran it again, we might get a different number. Some people, the reason I do this is about, and this room is very smart. So I fooled almost no one. But to a general audience, about a third of the room expect the numbers to come out in the conventional order of 1, 2, 0, 1, 2, 3. There's no reason because it's all happening in parallel. It's just whichever thread gets to write into the standard out first is the one that wins, and that's the next line. And so if you want things in a specific order, you have to do special things to do that. Yes. That's 2 slides smushed into one. The next thing we're going to look at is scaling. And so Tom has helpfully provided us with a file called pi.c. It's in that example code directory if you found it on GitHub or cloned it. And we're going to compile it again with the fopenmp flag, and we're going to give it level 3 optimization. We're going to call the output pi.exe. It's going to calculate pi. That computation has been done. We know what pi is. The purpose of this exercise is it's a sort of dummy workload that takes up some computation. So doing some random number stuff and some squaring and some square rooting and some math operations. And to get it to take a significant enough amount of time, we had to do a billion of them. 1 billion guesses of what pi is. The way this works is you imagine throwing at a 1 meter square, dartboard. So there's a 1 meter square and there's a circle completely in the middle of it, touching the edges. And so if you threw darts at random at that dartboard, a large fraction of them will be inside the circle, some fraction will be outside the circle. If you do that enough times and look at the ratio of it, you get pi. So that's the calculation we're doing. It could be anything. It's just one that generates enough computation for us to look at it. Sorry, I messed the slides up. What we would like you to do is compile the pi program, pi.c, with GCC, and run it on various numbers of num threads. OMP num threads equals some numbers. See if you get, ideally you should get similar number of pi each run, so the output of your simulation shouldn't depend on how many cores you ran it on. You would be surprised how often that is not the case. So you should get pi, and it should take a different amount of time depending on how many num threads you're using. So give that a go. Stick your hand up if you're having difficulty. This isn't in the slides, but I'll share that a shell trick. If you proceed, so the command line would normally be pi.exe. You can proceed it with a shell variable equals value thing, and it will set it for just that one invocation of the shell. So this one time I run it, I've got num threads equals 1. Yeah. Took 9.8. The other thing you can do on Unix is you can use the time command. So if I said sleep 2, it's going to sleep for 2 seconds, and then it's just going to give me no output. If I said time sleep 2, it should hopefully tell me it took about 2 seconds of what we call wall time to run. It's actually given us 3 values there. So it took 2 seconds as we would measure it on a wall clock. It took 2 milliseconds, 2 milliseconds of time on the CPU, and 4 milliseconds from the operating system. Yeah. So if we do this, Tom reckons it's about 10 seconds. So I'll go up to the microphone to get it for the recording because that's a good question. If you've got 4 hardware threads of execution, 4 cores, say, how many OpenMP threads can you have? As many as you like. It won't go any faster if you oversubscribe. Now, maybe your threads are hyperthreading and you've got 8 virtual threads. It won't go 8 times as fast. It might go 5.6 times as fast. Maybe you'll be lucky. So sometimes oversubscribing wins you a fraction, but not much. This is a real problem when you have nested things, when you have one OpenMP thing calling another OpenMP thing. So if you had 76 cores on a node and you run the Intel version of Python with Intel Math Kernel Library, it'll start up 76 Python interpreters, each of which start up 76 threads when they're doing the Math Kernel Library stuff. And it runs really, really slow. It runs like 100 times slower than it would have if you'd restricted it to the actual hardware resources you had available. So it's a problem to look out for. So we've got about half the room doing the exercise. That's good. Here's one I prepared earlier. So when I ran this a while back, I ran it on 1, 2, 4, 8, and 16 cores. I used the bash syntax for a loop and set num threads and used that time command by, I just pulled out one of those 3 numbers, the execution time. So on one thread, it took 978 seconds. 9.2, that seems good. It's less, so we're using, oh, yep, more compute resources, but we're getting, how do I turn that off? What is this? Anyway, you can see this. Hopefully you can see that. So one thread, 9.78 seconds, 2 threads, 4.92 seconds, 4 threads, 2.46 seconds. That's good. We're giving it more compute resources and it's running faster. 8 threads, 3.7 seconds. Uh-oh. And this is a question from the back of the room. How come it ran slower when we gave it, more hardware to work with? And it just gets worse. When I gave it 16 threads, it took 5.76 seconds. So if I run that, first. And so there's my data frame of results. Here's my graph. You are allowed to give me feedback about my Python source code. Have I put the right number of comments in there? Is it nicely formatted and indented? Anyway, that's the graphical representation of what we got. So we started on one thread, it was okay. 2 threads, nearly twice as fast. Unfortunately, it's suppressed to 0 on this axis, so you can't quite compare those. 4 threads, and then it gets slower. What would we expect? So what speed up did we get? Going from 1 to 2 threads, we got 1.98 times faster. So that's almost what we would want. Going from 2 to 4 threads, we got 3.97, still pretty good. Only a few percent off perfect. Going to 8 threads, we were at 8 times speed up and got 2.6. Yeah, 16 times 3. That's barely better. In fact, it's not better than using 2 threads. 16. What we would want, so that's speed up ratio. What we would want is the ideal speed up to be, speed up equals the number of cores. And what we got. So the question is, why will this happen? It used to be in the industry, we called problems like this embarrassingly parallel. We were embarrassed that it was so easy. People say that that's a bit exclusionary, and we would call it pleasingly parallel these days. So that's what we've got a pleasingly parallel problem. So we should get ideal speed up. We don't. One of the things that's happening is the operating system is designed for running enterprise workloads, and it shuffles things around the computer to optimize for throughput rather than performance. And so our Pi program, when we had one thread, it might have started on one core, might have moved to another core, that's fine. When we had two threads, they might have moved around cores in the process. When we had 16 threads, they might have moved around. Every time a thread moves, it loses its cache. So the cache values were on the old core, now it's on a new core. It's got to fetch all that data from memory again. So there's an overhead of moving the cores around. So normally what you want to do is pin the processors, make sure that the core sticks to the process sticks to the physical core. Other things that slow down OpenMP things, the design of these servers these days, to make them economical and make them buildable, they had to sacrifice the nice property we used to have, which was it took the same amount of time to get from a compute core to main memory, no matter which core you're on. Nowadays, you might have two sockets, two CPUs in a server. They can each see all of the main memory, that shared memory thing we were talking about earlier, but it might take longer for, say, the left-hand processor to access the memory on the right-hand side of the server and vice versa. So the length of time it takes to access memory is non-uniform. What was the other thing I had? The right answer to this question, how do we, why is it not running as we would expect, is not to guess, not to do what I'm doing now, because surprisingly often, even for experts, our intuition is wrong. The answer is to measure it with profiling. I'll mention some profilers later. So I was talking about shared memory in a single node. CSD3, it's got thousands of nodes. We can do a much bigger computation, but we have to switch the programming model. We have to add a programming model because OpenMP, at least most versions of it, the newer ones do the distributed program. OpenMP 6. Yeah. Up until now, OpenMP within a single node. There is another programming model I mentioned, MPI, short for message passing interface. And again, that's a standard, and there are differing implementations of it. But now the implementations are in libraries rather than in the compiler. So you need an extra piece of software. Examples are OpenMPI, which is confusing because we're just talking about OpenMP, but those are two different things. Even I confuse them. OpenMPI is the MPI implementation. There's another one called MPitch. If you're using a Cray system, Cray's MPI is a version of MPitch. If you're using our system today, we use Intel MPI. We do actually have the other ones available. You can swap them out, but the recommendation currently is to use Intel MPI on our system. What does an MPI program look like? So before we had directives, now we have library calls. Again, apologies if C isn't your thing. The line 2 you would normally have in any old C program that's doing I/O. Line 1 is what you need if you're going to be doing MPI. You need to include the MPI header. Then you need to make the very first thing you do before you do any other MPI stuff is you have to call MPI init. Person I copied this program off didn't fill in argc and argv. You can pass argc and argv into MPI init, so it's easy the rest of the command line you launch the program with, but anyway, that's not important right now. So similarly to OMP num threads and a variable that you can get access to inside your OpenMP to tell you how big a computation you're doing, in MPI, it's MPI com size will tell you how many MPI ranks there are. Ranks, tasks, same thing, they're just different standards, they call them different things. And then there's another call, MPI com rank will tell you which particular one you were. So if you launched 64 MPI ranks, you've got 64 versions of your program running, and in one of them, MPI com rank will return 0, and one of them, MPI com rank will return 63, and others are going to return different numbers, but they'll all be unique. Processor name here is just so that we can look at the output when we run this example program, the hello world, and know where we were running. It was easy to know where we were running when we were doing OpenMP because it was on the server we started it from. There was only one. In MPI, you could be on any number of servers. And so what we're going to print hello world from processor, some number, rank, some number out of some number. And the very last thing you do before you finish an MPI program is you call MPI finalize. So we should have MPI hello.c in the repository. The difference here is even though we're using GCC to compile it, we're going to call it a different name. So MPI CC is a wrapper around whatever your C compiler is that does all the magic that's needed to make the MPI program compile and linked. First stage is to run MPI CC on the hello world. The second thing is the way you run it is you have to launch it with a special command. You'll see this written in documentation quite a lot as MPI run. These days we call it MPI exec. The reason was different implementations had different flags to MPI run, and the MPI people said, we're going to standardize it so the flags are all the same. So MPI exec is the standard one. And so the NP argument tells you how many ranks you want your MPI program to run on. So similar to setting OMP num threads environment variable. So there's a little less hand-holding in this exercise, so we might need to wander around the room and help you write your job script. Build MPI hello.c, and then we want to submit it to we could run it on the login node. So you could do that line there, MPI exec minus MP equals 4 on the login node. That'd be fine. I wouldn't want you to do much more than 4. Running stuff on the login node is really for very, very quick, small tests. If you're running MPI, it's because you want to run a really big program. And so we want you to write a job script to launch it on 2 nodes. I would have said 2 nodes, 2 cores per node, but it's nice to have prime numbers when you're multiplying things together that are sort of orthogonal. So then when you're debugging, you can look at the output and know which of the things you change to get what. So that's why I've said 2 nodes, 3 cores per node. So have a go at that exercise. If you are confused, I don't blame you. Stick your hand up and one of us will come around and explain. Yes. It's almost, I said it's almost like a thread. It's just there were different standards bodies and they called them different things. But when I'm talking about MPI, I'll call them ranks because that's what all the documentation about MPI says. When I'm talking about OpenMP, I'll call them, I should be calling them tasks. Okay, it's 10 minutes to, so we have 10 minutes to coffee. There's only one more exercise and it involves no programming, but you do have to sit through about 9 minutes and 30 seconds of me waffling. So I'll get started now so we can get to the exercise before coffee. So we saw a couple of programming models there for using high-performance computing resources. So now you can use all the cores in one node. Now you can use all the nodes on one HPC cluster. But I've only told you about how to use CPUs. There are other sorts of computing hardware available. in general, they're called accelerators. You probably know there's GPUs, that's the most common one. GPU in the name, graphics processing unit, started off just for doing graphics calculations, but it turns out that the things you need to do for graphics calculations, like multiplying matrices by vectors and scaling and adding constants, is exactly what you need to do in scientific computing. And so these are well optimized for scientific computing, just not well optimized for programmability. And so again, there's no single programming model I can give you that everyone uses and will work on everyone's hardware. If you have NVIDIA hardware, as we do in CSD3, the Ampere partition is NVIDIA A100s. The programming model to use is CUDA. If you have AMD GPUs, as we might do in the future, the programming model to use is HIP. AMD did us a favor. They just copy-pasted everything in NVIDIA and replaced the Q with ROC and the CUDA with HIP. So it's actually very easy to port. If you have Intel GPUs, as we do in CSD3, you're out of luck unless you're doing AI work. If you're doing AI work, PyTorch and TensorFlow are ported, and it should just work. If you're doing simulation stuff, unfortunately, CUDA doesn't work on NVIDIA's CUDA doesn't work on Intel's GPUs. It'd be nice if they played together, but they don't. Intel recommend a thing they call OneAPI, which is their implementation of SYCL. SYCL is the generic one which works across lots of bits of hardware. The American National Labs had this problem. They came up with multiple solutions. One's called Raja. The one that seems to be more winning is called Cocos. That's an abstraction layer. If you write using Cocos tools, Cocos will then do the translation to CUDA or SYCL or other stuff in the background for you. And the OpenMP people also didn't want to be left out of the fun. You can do offloading using OpenMP to GPUs. Bad news, and we already saw it. I already plotted the graph. We had a pleasingly parallel program that should have had ideal scaling and it didn't. It dropped off. This is a general problem. You will always have this where some fraction of your program, this is actually 1 minus b, the fraction of the program that is necessarily serial can never be parallelized, can't be speeded up. So that might take, on a few cores, that might take 1,000th of the runtime. On 100 cores, it might take 10% of the runtime. On 1,000 cores, it might take half the runtime, because that's the difference. No matter how many cores you give it, that necessarily serial part will always take the same time, so take a larger fraction of the wall time as the wall time goes down. This is an observation Gene Amdahl made, and so it's called Amdahl's law. And so that's the graph of it I stole from Wikipedia. And if you've got 95% of your program is parallelizable, that's cool. Pull up the map here. So you see we've got 256 client being able to do sort of that bottom here, but we're still only going 18 times as fast. And that's with 95% of your program being parallelizable. And if the fraction is smaller, the use is even worse. Good news. You can get, if you've got a big enough program, big enough problem, you can get around it by splitting it into more and more chunks. So there are two different types of scaling you'll hear referred to as strong scaling, which is the thing you do with Amdahl's law, where we just gave the same problem size more computing resource. With Gustafson's law, weak scaling, we increase the problem size as we increase the amount of computing. And so then we win back some of the stuff we lost with Amdahl's law. Debugging, I was going to show you how to launch a debugger in a job script. So debugging on the command line is easy. You type GDB in your program name. It's a little bit more tricky if you're doing it in a bash script. We'll have to save that for, you have to come back next year. Just do that. If you would like to talk about debugging parallel programs, Tom is your man. He loves it. And you've got a session after this. Cool. As I said before, don't try and rely on your intuition to know why something's not running as you would expect. measure it. So the tool you need is called a profiler. This is a survey from 2003. If you use a profiler, you'll be ahead of 73% of programmers, or 82% who don't use them. So judging by the stream, I know you'll be smarter than them. So those are the names and some links to some profilers. Intel vTune is the one we use on our Intel system. The remainder of these are open source. I really like the name of the last one, which is pronounced Liquid. It stands for like I know what I'm doing. True story. If you want, these are really good for programming the execution in the CPU, telling you whether you're using the vectorized instructions, telling you whether you're using the cache efficiently or not. It's not, these ones aren't so good about telling you if you're waiting on I/O, if you're reading and writing, and you're not doing the reading and writing in the most efficient manner. If you want to do that, I was going to have an exercise on using Darshan again. Come back next year if we might do Darshan. We've got 4 minutes. Great. So we're here as part of the DESRI program or ICCS to talk about how we do computing and the climate. We care about the climate. We care about not putting more CO2 into the atmosphere, not making the problem worse. Bad news is we haven't found out a zero energy way of doing computing. Computing takes energy. We have to provide that somehow. Usually that involves emitting carbon dioxide. So we would like to minimize the amount of that we do. Yesterday we heard about the top 500 where we run LinPath and see how fast we can run it. It used to be a full stop at the end of that sentence. That was the competition. See how fast we could go. For the past 10 years or so, I got that wrong. I've actually got a German club talk on YouTube about this. Wu Fang from Virginia Tech started looking at the amount of energy that was being used to do this, and so came up with an alternative list, the top 500 value score, divided by the amount of energy it took when you were doing the run. So you get a measurement in flops per watt. And so that's now a good competition. We came third in the world a few years ago on our Ampere nodes. We were the third most efficient supercomputer in the world. With 34 gigaflops per watt. The state of the art's now nearly 100. I think it's about 78 or so. So this now gets announced at the same time on the same conference as the top 500. So people are finally caring about it. There is a chap at the University of Cambridge called Loic Lanalog. If you follow the green algorithms link there, you'll see he's actually hiring at the moment. And he has an energy calculator, so you can plug in some values and see how much CO2 equivalent your computation emitted. My former boss did the same thing. His calculator is called How Much Is Enough. Again, with the profiling, you can profile to look at, you can either sort of optimize for speed or optimize for energy, and those are slightly different things. So a first order approximation optimized for speed, that will get you much more energy savings, but then there are some other things you can do. Use reduced precision. So do you really need 64 bits all the time? So there's some interesting work going on by the HPC research group at KAUST on when you can use low rank approximation, how you can change the algorithms to deal with smaller data formats. We may need to do that anyway, because the HPC market isn't big enough to drive silicon design. Silicon design is being driven by the AI people, and the AI people don't care about 64-bit floats. So if you've got a Grace Hopper CPU from NVIDIA, you buy the next one, the Blackwell, your code doesn't actually run any faster. There's all the extra silicon they put in Blackwell is just for AI. They kept the same number of execution units per floating point 64. And yeah, think about your campaign in computing. Do you need to run 10,000 jobs or put 1,000 to do? If you were smarter about where you were looking in the problem space, and so Tamsin mentioned Latin hypercube sampling yesterday. There's some Henry's not here, but one of our colleagues, Henry's got some good advice on using stats. You can be smarter about your experiment design to reduce the number of expensive computations you use. So just before tea or coffee, the final exercise is go to the Green Algorithms site and let's try and estimate the computing resources which we reserved for us, which was 4 nodes, 76 cores of, and the closest thing on Loic's calculator is the Xeon Platinum 8268, 512 gigs of RAM. We're in the United Kingdom, and that matters for the carbon intensity of the energy we're consuming. And the power usage efficiency of our data center is actually really good. The ideal number there would be 1.0. 1.1 is very, very good. Plug those numbers into the calculator and see if instead of reserving those nodes for us that are being used flat out, those 4 nodes and 6 cores each flat out for 3 hours, how much CO2 would that have emitted? You have to ask your data center provider to tell you what their PUE is. And so it's the power usage effectiveness, it's how much power gets delivered to the computing equipment versus how much power went into the data center. So some of the extra power gets used for cooling. So about 10% of our energy is used for cooling. You also have losses in the uninterruptible power supplies. You have losses in the power distribution. So in our data center, we're using conventional power distribution, 240 volts to the servers. In some data centers, they convert down to 48 volts in bulk, and then send 48 volts to the servers. That's slightly more efficient. So yeah, there are things you can do in your data center that will lower that. Yeah, we're doing that as well as we can. No, it's a ratio of energy input to the data center versus energy going to the computers. So if you had no losses on the way, it would be one amount of energy going into one amount of energy in the computers. No, you'd have to multiply them out. So 300, yeah. So on CSD3, the CPUs are generally not idling. Yeah, we've got, as we saw yesterday, 22,000 jobs in the queue. If we hadn't reserved these, they would be running, people's code, hopefully, near 100% efficiency. So on CSD3, we do sharing. So if you use 4 cores, that's fine. The other cores will get used by other people's small jobs. If you reserve an entire node, if you do node exclusive and only use 4 cores, then it's really bad. Yeah. That was it. Thank you very much for coming. Come back next year.